interpret complex numbers through geometric representation. Next, write complex numbers in rectangular, polar, and exponential forms. Convert complex numbers into different forms and perform basic algebraic manipulation with complex numbers. Okay, so for the complex numbers, or what is the definition for complex numbers? So the when we actually combine a real number and an imaginary number, we get the what we call rectangular, or we get the what we call rectangular complex number. Okay, or this is a type of complex number that is labeled or named as rectangular. So a plus bi, wherein a is the real part and bi is the imaginary part. Okay, that is the imaginary part. So a is the real part, bi is the imaginary part. Okay, so a and b here are both real numbers. Okay, a and b are both real numbers, and I here is what we call the imaginary, and that imaginary is equal to the square root of -1, or any number. So the square root of any number is, or negative of any number is um imaginary. Now, we have the different forms of complex numbers. We have the rectangular form, we have the polar form, or the what we call trigonometric form, and we also have the exponential form. Okay. In other books, these forms are separated into four forms, or four types. Actually, in other books, polar and trigonometric are separated. They are interpreted in a very different way. So actually, we can also do that later on, but for now, we will just be focusing on rectangular form and polar form. Okay. So if you have your EEM, or if you have your the advanced engineering mathematics, or the what we call the EEM 001, so you might have encountered this, that a polar form and trigonometric form are two different entities. Okay, but in other books they can actually be with the same entity, because it's just they just differ based on the interpretation. Okay, so for the rectangular form first, we go on to this one. So on the rectangular form, it is where our complex number is equal to a plus bi. So the rectangular form of a complex number is a sum. Okay, it is a sum of two terms, the numbers real part and the numbers imaginary part multiplied by the imaginary. So we can also actually plot, okay, plot a complex number given in rectangular form in the complex plane. So we have a complex plane here on the right side of your screen. So the real and the imaginary parts determine the real and imaginary coordinates of the number. So if you are going to observe a certain Cartesian plane, or a certain plane, on the x-axis, that is our real axis, and our y-axis, that is our imaginary axis. So we both have the positive real axis and the negative real axis, and we also have the negative and positive imaginary axis. So let's say, for example, if you are given here 5 plus 4i. Okay, 5 plus 4i. So 5 will be plotted herein on this part, on the horizontal part, where in 4, okay, 4 will be plotted on the vertical part. Did you get it? So if you are going to plot your 5 here and your 4 here, so the ending point, or the meeting point of both numbers, are what we call the rectangular form, or is what we call the rectangular form of a certain complex number. Okay. Now we also have the polar form, or the trigonometric form. So in other books, polar form is just this one, and trigonometric form is just this part. Okay. So that's why they are separated into two entities. But if you are going to at least understand this one, that r angle theta is also equal to r cosine theta plus imaginary sine theta, or in other books this is also interpreted as r cis. Okay, cis is spelled as cis. Okay, r cis theta, that is basically just equal to this form. Okay, because cis is just equal to cosine imaginary sine. Okay, and cis is just equal to angle symbol. That's why herein I just combined them because somehow they are the same. Okay, did you get it? Any questions so far before we proceed? Question? Are you still following? Are you still following? Okay. Okay. So we have now the polar form, as I've said. So the polar form, which is equal to C or R angle theta, wherein R is the distance or the magnitude from the origin, and the theta is the angle measured counterclockwise, okay, or from the positive x-axis, is still the imaginary, or yeah, is still, or x-axis is still the imaginary, the x-axis is still the real axis, and the y-axis is still the imaginary axis. So as I've said a while ago when we discussed the rectangular form, that the horizontal axis is the real axis and the vertical axis is the imaginary axis. Same as true, same holds true with this kind of situation, or with this polar form. Okay? So since we have the r angle theta, so this is our r, the length, okay? So if this point is our rectangular form, and if we trace back this point from the origin or back to the origin, the length of this line from the origin up until to the point is the r, or the distance, or the magnitude. Okay, then the angle subtended, okay, the angle subtended from, okay, from the that certain line, from that certain line here in up until to the positive x-axis, that certain angle is, or will be measured counterclockwise. Okay, so that would be our angle now. Okay, that would be the direction of our line. Okay, so this is now the polar interpretation of this one. Next, we have the exponential form, but I will no longer discuss what is an exponential form because that would be covered on your EEM 001. So we will just be covering how can we at least convert polar form to rectangular form and rectangular form to polar form, because that is very necessary later on. Okay? So this is now the conversions between forms. So we are going to convert rectangular to polar and vice versa. So on the right side corner, or on the right side of your screen the uh is the graph, the combined graph of your polar and rectangular. Okay, so on your rectangular form, which is written as a plus jb, okay, a plus jb, so the imaginary part is the b here, and the real part is the a here. Now on your polar form, you have your c angle theta, right? Your c is the magnitude, this one, and your theta is your angle. Okay, so basically this whole graph is a combination of rectangular and polar form. So what can you observe on the graph? What does it make? What can you observe on the graph? What does it make? By combining the interpretation, or the geometric interpretation of polar and rectangular, what can you make? Or a right triangle. Very good, Russell. Okay, so we have a right triangle here. So by simply observing, or by simply seeing this kind of graph, we can say that it forms a right triangle. And on a right triangle, what does it involve? We can actually use what when we are dealing with right triangles? What comes to your mind when we deal with right triangles? The Pythagorean theorem, very good. And the trigonometric functions. So through Pythagorean theorem and through trigonometric functions, we can actually convert between forms. We can actually convert rectangular to polar and polar to rectangular. Okay? So in this case, we can just actually, let's say, for example, if you are given rectangular, okay, you are given a rectangular form. So it means that you're given are just A and B. Okay, it means that C and theta are missing, and we are going to find it out. Okay, we are going to find C and theta. Now, if you are given the adjacent side and the opposite side, how can we get for C and how can we get for theta? So, of course, if C is missing and our given are A and B, what would be the equation in order for us to get for C? What would be the equation? What do you think will be the equation? Okay, very good. That our C is equal to the square root of A squared plus B squared. So basically, that is just the Pythagorean theorem, correct? That is just the Pythagorean theorem. So Pythagorean theorem, it means that the square of your hypotenuse is equal to the square of your adjacent side plus the square of your opposite side plus the square of your opposite side. So basically, if you are going to get for C, that is square root of A squared plus B squared. So you can now get for C. What about if you are going to get for theta? Given A and B, you are going to get for theta. What would be the equation? Okay, so if we are observing theta here, okay, the angle here, B is what side? B is the, basically is the opposite side. What about A? A is the adjacent side. So if it involves opposite and adjacent, we can say that the tangent, okay, tangent of the theta is equal to B opposite over adjacent. So that is tan theta is equal to B over A. Just like what Francis have said. Okay, so basically we can already get for the theta that theta is equal to the arctangent. Okay, theta is equal to the arctangent of B over A. Did you get it? Did you get it? Are you following so far? Okay. So since we already know how to convert rectangular to polar, we now go on to polar to rectangular. So the given now is C and theta. We are going to find out A and B. Okay? So if you will be imagining that C and theta are given, how can we find for A? How can we find for A? We can use the trigonometric functions, correct? So if we are going to observe theta and we are going to find out A, what is the relationship between A and C? What is the relationship between A and C? A now is the what side? Is in what side of the angle? Hmm? A is what side of the angle? This is our angle theta. What is this? A is what side? Is it opposite, adjacent, the hypotenuse? What is it? Is A the opposite? Are you sure? This is our theta. This is our theta. What is A? Is it adjacent, opposite, or hypotenuse? Basically, our hypotenuse is just C. This is the only hypotenuse on a right triangle, right? Okay, so basically this is adjacent. So we have a given of hypotenuse because C and theta are given, right? So C or our hypotenuse is given, then our adjacent side is also given. Okay? So if we are dealing with adjacent side and hypotenuse, what certain trigonometric function are we going to use? Cosine, very good. So if we are going to get the cosine of the theta, okay? We are going to get the cosine of the theta. What is the result? The cosine of theta is what? Equal to adjacent over hypotenuse. So that is equal to what? Is it A over B? Cosine, the trigonometric function cosine is, can you remember it? So let me just use my pen so that you can follow. Okay, so we have the right triangle, right? This one. So we have the theta here, then we have your A here, we have your B, and you have your C. Okay? Now, what I'm talking about a while ago is our only given is C and theta. Then we are going to find out for A. So if we are going to find out for A, and A is the adjacent side, this is now the adjacent side, and C is the hypotenuse. Remember our SOHCAHTOA. Remember, this is a high school lesson, my dear students. Okay? That when you use your sign that is opposite over hypotenuse, when you use your cosine that is adjacent over hypotenuse, and when you use your tangent that is opposite over adjacent. Okay? So since C is the hypotenuse, okay, and A is the adjacent, what is the most applicable trigonometric function? This is cosine, right? So cosine is the most applicable trigonometric function. Therefore, we can say that the cosine of your angle is equal to the adjacent over hypotenuse. Therefore, that is equal to your A over C. So basically, we can now get for A by cross multiplying. Therefore, our A is just equal to your C cosine theta. So you can now get for A given C and theta. Did you get it? Did you get the formula? Okay. Now, in other way situation, how can we now get for letter B, or how can we get for the parameter B? It is, we can use this since B is the opposite of the angle. So that is, we have a given of opposite and hypotenuse. Basically, that is sine theta. And sine theta is equal to opposite over hypotenuse, and that is B over C. Now, B is equal to our C sine theta. Did you get it? So in terms of A, or in terms of C cosine theta, and in terms of C sine theta, we can get both A and B. So if you already got A and B, you are just going to plug it in onto the equation, which is C is equal to A plus JB. So if you get 1 on A and if you get 2 on B, that is 1 plus J2. Gets? Okay, now let us use your calculators. I hope you have your calculators with you. Do you have your 991 ES Plus or your 570 ES Plus Casio? Because that is the one I have here. But of course, if you have your calculators, your own calculators, your own version of calculators, I want you to please familiarize how can you use your calculators, because we cannot deal with each and every calculator. Okay? So you have your own weapon. So please master how can you use it. Okay? And don't let your weapon kill you. Okay? Kill somebody else onto your weapon and not yourself. Okay? So familiarize your weapon, familiarize your calculators in terms of complex numbers, because I tell you, this is the start of using complex numbers. And up until you graduate, you will be using complex numbers. Until you would take the board exam, you will be using complex numbers. So if I were you, if your calculators do not have the complex function, okay, please upgrade onto a certain calculator or invest onto a certain calculator that has one. Okay? So, if you have your 570 ES Plus or if you have your 991 ES Plus with you as of now, I think you can actually um follow my instructions, okay? So that you can at least use your calculators. So, of course, please set up your calculators first, turn it on. Then upon turning it on, press shift. After shift, press 9, the number 9. Then you will see on your calculator the clear. with question mark, clear question mark, then 1 setup, 2 memory, 3 all. Then just press 3. 3. Then it will appear on your screen that reset all with a question mark. Then you will press equal yes, AC cancel. So you will press equal, that is yes. Then reset all, press AC key. Okay? So now your calculator is on your default format. Okay? It is now on your default format. So since it's already on your default format, we can now go with the complex mode. Okay? So how can we go on to the complex mode? Okay? So just press mode on the left side of the on button. Okay? On the left side of the on button, you have your mode there. So 1 stands for computer, 2 stands for complex, 3 statistics, 4 base N, 5 equation, 6 matrix, 7 table, and 8 vector. So you will just press 2. That is the complex mode. Then you will see on your screen, on the upper part of your screen, the CMPLX code. It means that your calculator is already on the complex mode. Are you following? Are you following? What about the others? Are you following? Who got the calculator with them? Okay. So are you all following so far? You are now on the complex mode. Okay. So let us continue. So since you are already onto the complex mode, okay, you are already onto the complex mode. Let us convert 5 angle 60 to rectangular form. Okay, 5 angle 60. So just type 5, then the angle sign is in the negative. Can you see the RCL? The RCL button on your calculator. Then on the upper part of your RCL, there is a parenthesis or parenthesis with a negative key inside. So if you will be seeing that on the upper part of that negative is the angle sign. And you need to shift or press the shift, then that button, the negative button on the upper part of the RCL. Okay, then you will see on your calculator the 5 and the angle symbol. And just type 60. Okay, so you can already see the 5 angle 60 on your calculator, right? Then just press equal. So upon pressing equal, you will see there 5 over 2 plus 5 square root of 3 over 2i. Okay? Of course, we don't want a fraction or we don't want a fraction or we just wanted a decimal answer. So what are you going to do is press the S to D button. The S to D button is on the upper part of the delete button. Okay? The S to D button. Then you will see there an answer. So what would be the answer? You type on the chat box the answer you've got. The whole answer. Okay, the whole answer. Just round it into 2 decimal places. Okay, so that is 2.5 plus 4.33i. Okay, don't forget the I because this is part of our equation. Okay, that is part of our equation. So that is 2.5 plus 4.33i. Okay? So that means that your polar form is already on your rectangular form, just pressing the equal. Okay? Just pressing the equal. Why is that? Because the default of your calculators, the default mode of your calculators, that your answers will always be in rectangular form. Okay? Will always be in rectangular form. Now, how about we convert now 6 plus J7 to polar form? How can we do that? So now, press AC button. Press AC button or on mode. Okay? Then type 6 plus 7i. Your I is the ENG. You can see there the ENG, then just press the ENG and it will I will already appear. Okay? So 6 plus 7i will be on your calculators. Okay? Then just press equal. Okay? When you press the equal, what would appear? Upon pressing equal, what would appear? Okay, it's still 6 plus 7i because again, the default of your calculator is always in rectangular form. So it is not yet converted. It is on the rectangular form as well. Correct? So what are you going to do is press shift. Upon pressing equal, press shift. Then press number 2. It will appear on your screen 1 argument, 2 conjugate, 3 r angle theta, 4 a plus bi. 3 there is the polar form, 4 is the rectangular form. So since we are going to convert your rectangular to polar, we will press number 3. Okay? So upon pressing number 3, it will appear on your calculator the ans, then with an arrow, r angle theta. Then just press equal. Upon pressing equal, you will see there the answer. But the answer is on the square root form. So what are you going to do is press S to D again. S to D so that it will appear as decimal. So what would be the answer? Can I see your answers? Okay, very good. So that is 9.22 angle 49.40 degrees. Don't forget the degrees. Okay? So can you now do it on your own? Okay, so let's have another example. Okay, do it on your calculator. Okay, so let us have now 4 angle 65. What would be the rectangular equivalent of 4 angle 65? 4 angle 65. What would be the rectangular form? Okay, very good. So that is 1.69 plus 3.63i, or we can actually write it as 1.69 plus j 3.63. Because in circuits 2, we are using j rather than I, because to avoid confusion between the current. Because as we all know, when we deal with circuits, I is equal to current. So in order for us to avoid that confusion, we will just be using j instead of I. Okay, so that would be 1.69 plus j 3.63. Very good. Now, what is the polar equivalent of 5 plus j20? 5 plus j20. Okay, very good. So that is 20.62. Okay. Angle 75.96. Very good. Okay. So since you already know now how to use your calculators, okay, I think we can already perform the addition and the subtraction of complex numbers. Okay. So let us now see how can we add complex numbers. Of course, using your calculators. Okay, so you are given A is equal to 1.41 angle 45 degrees and B 3.61 angle negative 56 degrees. Determine A divided by B and solve for A multiplied by B. So what is A divided by B and what is A multiplied by B? So let us first determine A divided by B. So you will be typing on your chat box the equivalent of A, so that is 1 point, or on your calculator, sorry, that is 1.41 angle 45 divided by 3.61 angle negative 56. Okay? Your answer should be in polar form. Okay? What is the answer in polar form? Type your answer onto the chat box. Polar form. Okay, very good. So the answer is 0.39. So that is 0.39, 0.39 angle 101 degrees. That is not negative. It should be positive 101 degrees. Okay, 0.39 angle 101 degrees. So let us now solve for A multiplied by B. So that is 1.41 shift angle 45 multiplied by 3.61 shift angle negative 56. Give me your answer in polar form. What would be the answer? Okay, so that would be 5.09 angle negative 11 degrees. Very good. Okay, 5.09 angle negative 11 degrees. Okay, can you now get it? So let us have now the addition. So you have addition here, 1 plus J1 and 2 minus J3. So determine A plus B and A minus B. So you have to determine what is A plus B and A minus B. And I want your answer in polar format. Polar format. So that is 1 plus J1 or 1I or 1 plus I plus your 2 minus J3. So what would be the answer on A plus B? Okay, very good. So we have 3.61 angle negative 33.69. Okay, very good. How about A minus B? So let's see what would be the A minus B. Okay, so we have 2 point. Are you sure? Make sure of your answer. We have, what is the answer, Russell? 4.12 angle 104.04. Why did you come up with 2.24? Still, we have 1 plus J1 minus 2 minus J3. Make sure that 1 plus J1 is in a certain parenthesis and 2 minus J3 is in other parenthesis. Okay, because they are different quantities. So it must be it must be written on your calculator as open parenthesis 1 plus 1i, close parenthesis, minus open parenthesis 2 minus 3i, close parenthesis. Then it will give you negative 1 plus 4i. Then you have to convert it into polar. And that would give you 4.12 angle 104.04. Are you following? Okay. Russell did get it. What about the others? Have you got the correct answer? Andrea, Jeremy, Francis, Reggie. Okay, the answer is 4.12 angle 104.04. Okay. So do you now understand how to convert complex numbers or how to perform the addition, subtraction, multiplication, and division of complex numbers through your calculator? And how to convert rectangular to polar and polar to rectangular? Can we now move on? Is complex numbers already clear on your part? Are you sure? Any questions before we actually move on? Any question? Clarification? Question, clarification before we actually moved on to our next lesson, on our next topic. No questions? Okay. So, our next topic today is the introduction to phasors. Okay, the introduction to phasors. So, since we have already done or we are already done with our review that complex numbers are also utilized in calculations of current, voltage, or resistance in AC circuits. Okay. So, furthermore, complex numbers are also used to express the magnitude and phase of your phase of impedance in an AC circuit. So you should at least share your learnings about complex numbers to your classmates through an infographic material. So I have tasked you last week to do, to do a certain infographic material. Have you done it? Have you done it? Okay, so to do your infographic material about complex numbers. So you should at least upload it later on your Canvas. I will be allotting a certain activity there that you can upload your output. Okay? So for today's intended learning outcome, okay, are review complex numbers in rectangular and polar form, Recall addition, subtraction, multiplication, and division using complex numbers, which is already done a while ago. Use phasors to represent sinusoidal voltages and currents. Determine a phasor diagram that illustrates phase relationships. Represent a sinusoidal voltage or current as a complex number in polar and rectangular form. Define time domain and phasor or frequency domain. Use the phasor domain to add or subtract AC voltages and currents. Determine the voltage and current phase difference for purely resistive, inductive, and capacitive elements. Then analyze impedances of purely resistive, inductive, and capacitive elements as a function of phase and solve impedance and reactance of a series RLC circuit. Okay? So we have the what we call phasor transform. So why do we use this what we call phasor transform? So to solve problems that involve sinusoids such as AC voltages and currents, we use the what we call phasor transform. So number 1, we transform sinusoids into complex numbers in polar form. Okay? Because sinusoids, they are given into the what we call, or they are represented by what we call differential equation, in a differential equation form. Okay? So in order for us not to deal with differential equation and just to deal with simply algebra or simply complex numbers, we will be transforming our phasors, okay, or we will be transforming our sinusoids, okay, sinusoids into phasor format. Okay? So we are now going to solve the problem using complex arithmetic. So what are complex arithmetic? That is addition, subtraction, multiplication, and division of complex number. And after that, after we actually solve for the equation, we will then transform back the result to a certain sinusoid again. So it means that we are using, or we are just using phasor transform in order for us to solve a certain problem easily. Okay? But of course, we will be transforming the result back onto its original form. So how's that? So later on I will be discussing with you how can we at least do that. How can we at least use this phasor transform? Okay, but of course, what are phasors first? So when we say phasor, a phasor is a rotating vector. So I believe you have already studied linear vector on your physics, correct? Are you familiar, still familiar with vectors? Scalars and vectors on your physics, physics 1. Have you studied it? Have you studied it? Okay. So when we say phasor, it is a rotating vector whose projection on the vertical axis can be used to represent a sinusoid. So as you can see onto the image, okay, on your screen, when we actually rotate, okay, imagine that we are rotating a certain line, okay, a certain line. If we rotate a certain line, it will result into a certain sine wave. Okay, it will result into a certain sine wave. And the length of the phasor, okay, the length of the phasor is what we call the amplitude of the sinusoid, or it is the maximum voltage, or it is the maximum value, maximum current of a certain sine wave. Okay, now the angular velocity of the phasor is the omega. Okay, it is the omega. On a linear vector, we call it velocity, but on a phasor, we call it angular velocity. It means it is the velocity on a rotating body, okay, or on a rotating vector. Okay, so as you can see there, we have the resulting sine wave, and this sine wave has different parts. Okay, again, our omega is what we call the angular velocity. Okay, wherein our omega, or our angular velocity is equal to 2 pi multiplied by the frequency. Okay? Again, I will repeat it. Our angular velocity is denoted by omega. Okay, omega, or simply the Greek letter omega. Okay, and our omega, or our angular velocity, is equal to our 2 pi multiplied by our frequency. Okay, so let me just unshare my screen so that I can at least explain it to you what are the parts of our sine wave. So we have our sine wave. Okay, or we have our wave here. So it is composed of actually let me change the color. Okay, so we have here the VM, or the maximum amplitude. Okay, in other books, it is called as VP. Okay, what is VP? Peak value. Okay, peak value. So we have the maximum peak value, and we also have the minimum peak value. So this one is the maximum peak value, and this one is the minimum peak value, or the minimum value of our of a certain parameter. So it's either a voltage or a current. Okay? So since that is it, so this is our value, this is now, okay, the maximum value from the maximum value down to our minimum value. That is what we call the VP to P, or the peak to peak value. Okay, the peak to peak value. So as I've said a while ago, we have the what we call angular velocity. And our angular velocity is equal to 2 pi multiplied by our frequency. Okay? Wherein on this certain sinusoidal wave, we have this length. And the length from the very start of our sinusoid up until its end, this is what we call the T, or period. Okay? This is the time that is actually consumed by our sinusoid to complete its cycle. Okay? So once the cycle is already completed, this is what we call period. And our period, T, is equal to our 1 over frequency. Therefore, we can already say that our frequency is also equal to 1 over our period. Can you still follow? Yes? Yes, Lawrence? Are you saying something, Lawrence? Are you saying something? Now, okay, so moving on, how can we write, or how our sinusoids are written? So sinusoids are written in a format, or on a certain format that is equal to, let's say, for example, if you have a certain voltage. Okay, you have a certain voltage. So your voltage now is equal to, let's say, 20 sine omega t plus 30 degrees. Okay? So our sinusoid now is written as this one, wherein our 20 is our VM, or our it is our maximum value of our amplitude. Okay? 20 is our amplitude. Let us label it so that you would know. 20 is what we call our amplitude. Omega here is our angular velocity. Correct? Then our 30 degrees here is what we call phase, or phase angle. Okay, this is what we call the phase angle. Okay, in other books, omega has its value. So it can also written as 20 sine 100t plus 30 degrees. So if it is written like that, therefore your angular velocity is 100. Okay? Are you saying something, guys? Okay. Okay. So, are you following? Are you following onto the discussion so far? Okay. So, this is now how we interpret a certain sinusoid. So, going back, let me just share again my screen. Can you see it now? Okay. Okay, so we have now the what we call representing AC signals with complex numbers. So by replacing, okay, by replacing our VT, okay, our VT is the sinusoidal format, or it is on to our time domain format. What I've discussed a while ago, or what I represent a while ago with the 20 sine omega t plus 30 degrees, that is what we call the time domain format. Okay, so we have two formats. We have the time domain format, and we also have the phasor domain format, or in other books it is called as a frequency format. Okay, phasor and frequency format are just the same. So we will be replacing our time domain format into our phasor domain format. So how can we do that? Of course, why do we convert, or why do we at least represent our time domain format into phasor domain format? That is in order for us to convert from differential equation format to simple algebra. So as you can see a while ago, the 20 sine omega t plus 30 degrees, that involves the differential equation format, which is on the time domain format. So we are going to convert that into simple algebra. And that simple algebra is the phasor format, or the frequency format. Do you understand? Do you understand what I'm saying about this? Okay. So of course, we have the formulas from trigonometry that we need to remember, because in converting, okay, in converting here in electrical circuits too, we need to at least memorize how do we convert cosine to sine, sine to cosine. Okay? Because every representation, that depends on the what we call convention. Okay? So if we are following the cosine convention and your given is in sine convention, you must at least remember that you need to follow your convention. So if your given is on the sine convention, okay, and you are following the cosine convention, you need to convert your sine to cosine. Okay? So you need to follow your own convention. It depends on the instruction of your activity. So if it is said there that follow cosine convention, it needs to be that your answer must be in cosine form, or it is in cosine format. Okay? So let us not waste our time memorizing this one, familiarizing this one. I will give you a certain technique, okay? A certain technique on how to deal with this one. How to actually convert sine to cosine, cosine to sine. Okay? So let me just again stop sharing. Okay, so when we are in our college, we have this what we call cross of life. Okay, because we always use this one on different formulas that we are applying on mathematics, on algebra, on complex numbers, and so on and so forth, and even on circuits. We have this cross of life. But for now, I will be giving you the one function of this cross of life, and that is the conversion between cosine to sine and sine to cosine. Okay? So this will be our format now. Cosine to sine. So this will be our cosine, will be our sine. And this will be our negative sign. This will be our, wait, this will be negative sign. This will be sign. Will be your cosine. This will be your negative cosine. Okay, so just remember this one. Remember how you will be label sign, or how you will label the cross. Okay, so basically this is a Cartesian plane. Okay, this is a Cartesian plane that has its own function. So if you rotate clockwise, that is plus 90. If you, sorry, where is it? Okay, that is plus 90. And if you rotate counterclockwise, that is equal to minus 90 degrees. Okay, so what I'm saying here, okay, if you rotate clockwise, or if you are on the clockwise direction, okay, let's say you have a cosine and you are going to convert to sine. Okay, so if you have cosine, you are convert to sine. So that is here. That is basically clockwise. So you are going to plus 90 onto the original setup. Okay? So that is, if you have cosine omega t plus theta, that would be sine omega t plus theta plus 90. Okay, did you get it? If you have a clockwise, that is plus 90. If you have counterclockwise, that is negative 90. That would be onto the angle. So I will give you an example here. Wait, let me just share the screen. Can you see it? Can you see the screen now? Okay. So we are dealing with this one, right? This is what I'm talking about. Okay. So let us just use this one. If you are going clockwise, that is plus 90. If you are going counterclockwise, that is negative 90. Since you have already this one, no need to memorize this one. Okay, no need to memorize this one. Now, if you have your cosine omega t plus 70 and your convention is sine, so it has been said on the instruction that our convention is sine, so you need to convert your given into sine. Okay? So since you have a given of cosine omega t plus 70, you need to convert your given into sine. So from cosine to sine, so that is cosine to sine, that is clockwise, right? So that is, or you should at least add 90 onto the original setup. Okay? So you have now your cosine omega t plus 70 degrees, which is your original, and you are going to convert it into sine. So that would be sine omega t plus 70 degrees plus 90. So therefore, it is sine omega t plus 160 now. Okay? So that is sine omega t plus 160. Therefore, if you want to convert cosine omega t plus 70 degrees into sine equivalent, the answer will be sine omega t plus 160 degrees. Did you get it? Did you get it? Okay. Now, what if, what if you have your sine omega t plus 160 degrees, okay, but now your convention is negative sine, okay, your convention is negative sine, or you want us to convert it into negative sine. So basically that is sine, okay, your sine now to negative sine. So that is two quadrants covered. Okay, if we cover two quadrants, therefore that is 180. So how will you actually determine if it is plus 180 or minus 180? So since you have your sine omega t plus 160 degrees and you have a plus sign here in, it means you need to apply the opposite of the plus, and that is minus. So therefore, that is negative sine omega t plus 160 degrees minus 180. So ma'am, if it is minus 160 here, we should add 180 here? Yes. Okay? So it must be the opposite of this one. So negative sine omega t plus 160 degrees minus 180. So that would give you negative sine omega t minus 20 degrees. So from sine, okay, from sine to negative sine, this is now negative sine omega t minus 20 degrees. But what if you use cosine omega t plus 70 degrees and convert it into equivalent negative sine? Will you come up on the same answer? Basically, it should be. Okay, or you should be coming up on the same answer. Okay? So if you have your cosine omega t plus 70 degrees, and you convert it, or you want to convert it into negative sign, so that is cosine to negative sign, so you will give, or you will be on the counterclockwise direction. It means it must be minus 90 on the angle. So that is negative sign, or our cosine omega t plus 70, so that is negative sine omega t plus 70 minus 90. So it will give you again negative sine omega t minus 20 degrees. So basically, you will just come up with the same answer. Okay? Is everything clear? Is everything clear so far? Question? Okay. So moving on, we have the using phasor to represent AC voltage and current. So looking at this sinusoid equation. So this is our sinusoid equation in time domain format. Okay? This is our time domain format. Determine Vm, or the maximum amplitude, and the phase offset. Okay? Our phase offset is the same as our phase angle. So therefore, our Vm is this one, and our phase offset is 30 degrees, or our phase angle is 30 degrees. So in order for you to determine for the root mean square value, or the RMS value, you should at least use the formula Vm, or the maximum value all over square root of 2. Okay? So if you are going to get for the root mean square, we can now convert our time domain format into our phasor domain format. So this will be our phasor domain format. So if you have 20 sine omega t plus 30 degrees, okay, so VRMS will be 20 over square root of 2, okay, and that would be our VRMS, correct? So that is now our phasor format. So in order for you to at least understand it more, or understand it in a deeper sense, let us have these examples. Okay? So express 100 sine omega t as a voltage phasor. So 100 sine omega t is in what format? 100 sine omega t is in what format? What do we call that format? Hmm? What do we call that format? 100 sine omega t. Are you listening? My EE22S1. Starts with letter T. What is the format? It is in time domain format. Very good. And on time domain format, we are on a sinusoidal format. Okay? So, we are now on the time domain format. Therefore, if the instruction says express 100t sine omega t, or 100 sine omega t as a voltage phasor, we are going to convert time domain to what format? Time domain to what format? Phasor domain format. The other term for phasor domain format is what? Starts with letter F. What is the other term for phasor domain format? Hmm? I've said that a while ago. The other name for phasor domain format. Hmm? Starts with letter F. Is it Fourier? Why do we got on Fourier? Huh? Frequency. Very good. So the other term for phasor domain format is frequency format. Take note of these terms, my dear students, because later on I will be asking you convert this time domain to frequency domain. And you will be like, what is frequency domain? What is phasor domain? So you should at least determine what are those different terms? What are those different parameters? Did you get it? Did you get me? Okay, and if you have any questions, and if our discussion is a bit too fast, and you wanted to uh for me to at least slow down a bit, please tell me. Okay, please tell me. Do not just say yes and yes and yes. Okay, are we clear about that? Do not just say yes. If you don't understand it, then tell me so that I could at least let you to absorb the first learning first, then we go on to the next, and we could slow down our rhythm. Okay? So moving on. So where are we now? Okay, so moving on, we have this one, express 100 sine omega t as a voltage phasor. So if we are going to express this one as a voltage phasor, so we have VRMS. Okay, so we need to convert our VRMS first. So in order for you to come up with the phasor domain value. Okay, so since we have the time domain value, where is okay. So we have the time domain value, right? And we have the phasor domain value or the format. So the time domain format is denoted by this one. And the phasor domain format is this one. So when it comes to current, that is like this. When it comes to current, that is like this. So our VT or IT is in the form of Vm sine omega t plus the angle, right? Or Im sine omega t plus the angle. Now, on the phasor format, this becomes VRMS angle theta. And that theta, the theta here and the theta here is just the same. Okay? So, no need to convert. We are just going to convert the VM to VRMS and VRMS to VM depending on the conversion that is going on. So, this will be IRMS angle theta. But on other books, especially if you have already browsed on the book or on the reference of uh what is the title of that, of Charles Sadiku. Okay, your reference book on your modules, if you have already browsed on it, okay, on that certain reference, they are no longer converting maximum value to VRMS or VRMS to maximum value because of a certain reason. And that is if we are going to, okay, I hope you would already understand this one. If you are going to convert VM to your VRMS, then at the end of the day, you are again converting VRMS to VM. It's just that you just lengthen the process. Okay, you just lengthen the process, but you will come up on the same answer if you would just stick onto the given itself. It's just like you have five. Okay, let's say for example, if you have a certain value. So let's say that certain value is five. And on the first start of your process, you divide 5 by square root of 2. Okay, you divide 5 by square root of 2. And at the ending process, you will now going to convert your answer multiplying it by square root of 2. It means you divide and you multiply square root of 2. If you multiply, okay, if you have 5 and you divide by it and you divide it by square root of 2 and at the ending process, okay, what is 5 divided by square root of 2? So it will give us 3.54. Okay, this is 3.54. And at the ending process, you are going to go back onto the original format. So in order for you to convert now your VRMS to your VM, you will again multiply it by 2, correct? Or by square root of 2 and you will come up on the same answer, 5. Did you get it? It seems like we are just canceling the process or we are just canceling the this process, the length of the process. Did you get what I mean? That's why on other books, they are no longer converting VM to VRMS or VRMS to VM because at the end of the day, okay, at the end of the day, you will just come up on the same answer on the short format. Okay? But of course, if you are not obliged, okay, if the problem says no need to convert or no need to come up with the time domain format, we are just converting back, okay? We are just converting back your answer into the time domain format if it says that you need the equation format. Okay? If you need the equation format, you can actually proceed on doing the shortcut rather than the long process. Okay, if you are obliged to do it or to come up with an answer of an equation or on a time domain format, but if the problem does not oblige you to come up with the equation or just stick with the phasor domain, you still need to convert VM to VRMS. Okay, because you will be stopped. Okay, you will be stopped on a certain situation that you no longer need to multiply back onto the same or you don't no longer need to multiply square root of 2 on your answer. It means you will not be going back onto the original setup. So therefore, there will be no canceling or there will be no canceling of the process. You will just stop there. Did you get what I mean? Did you get what I mean? Don't worry. Later on, I will be discussing more of this one. I will be discussing more of this one so that you can at least visualize what did mom says. What did mom says about this process and all. So that you would understand that you can do this, you can do that, you can do this and do that. Okay? So I want you to learn both the convention. If we have the cosine convention or if we have the sine convention. I want you to learn both of the process. What is happening and what will be the answer. So either you take the cosine or you take the sine convention, you will come up on the same answer. Okay? They just differ on the angle because sine and cosine differ on the angle. Okay? But you would come up on the same answer naturally. Okay? Okay. So this is what I'm talking about a while ago. So if you have your time domain format, this is ET or EMF at the time domain because EMF is also our voltage. Okay, other terms for voltage, I've already discussed this one on your circuits one. If I am your circuits one, what are the other terms for voltage? Other terms for voltage. Anyone? Hello? What are the other terms for voltage? the other terms used for voltage. Take note of these terms, my dear students, because these are very important. Because there are some problems on your board exams that is not directly said that you should at least come up or look for the voltage. No, they are using different terms. And if you don't know about these terms, okay, basically you will not get the correct answer because you don't know what are you going to compute. Energy is different from voltage. Charge is different from voltage. They are three different entities, and current is different from voltage, my dear students. Oh my God. They are Current is different from voltage, as well as resistance is different from voltage. The other term for voltage is what? On other books, they call voltage as potential difference. Remember that. Potential difference. Or EMF, very good. The electromotive force. Potential drop is also voltage. Potential itself is also voltage. Potential difference, potential drop, EMF, electromotive force, that is all voltage. Okay? They are all called as voltage. Did you get it now? Did you get it now? Because later on, you might actually encounter a certain problem that it says, or that says, what is the potential difference in the circuit? It means that you are going to find out for the voltage and not for the current, not for the energy, not for the charge, but for the voltage. Did you get what I mean? Hey, did you get what I mean? Okay, so since we have this one, we have a representation of this one. Okay, so we have the time domain format. So our time domain format is this one, that ET. E stands for EMF. So ET is equal to EM, or the maximum value of our amplitude, sine omega t plus theta. So you are going to convert it into phasor domain format. What is again what is again the other term for phasor domain? What is again the other term for phasor domain? Frequency domain. Very good. Take note of these terms. Okay? So in order for you, of course, to convert your time domain to phasor domain, you should get first the VRMS, or the root mean square value. And that is dividing your maximum value to square root of 2. So once you've already get the VRMS value, and you already came up with your phasor domain format, that is VRMS angle theta. Okay, you will now again you will now again convert back your VRMS to your VM. Okay, now how will you do that? Of course, you will be multiplying now your VRMS to square root of 2. So you will again be going back onto the original format. That's what I'm telling you a while ago. Okay? So before writing the sinusoid equation after finding the phasor, okay, you need to convert the phasor magnitude back to the sinusoid representation. And that is multiplying the phasor magnitude by square root of 2. Okay? Rule of algebra, if you divide and multiply the same number onto a certain number, that is just multiplying a certain number by 1. You will come up with the same number, or on that certain number itself. Okay? Just like what I've told you a while ago. If you divide 5 by square root of 2, and the answer, and you will be multiplying the answer by square root of 2, you will come up by 5. Did you get what I mean? Did you get what I mean? Okay. So I think let us just stop it for now. Let us just stop the learning for now so that you can at least absorb what did I discuss on this certain moment, or what did I discuss during the day. Okay? So I want you to at least go back, okay? Go back with all of the discussions today, okay? All of the discussions today so that you can absorb what I have said. Okay? You can absorb all of the learnings that we have done today. Okay? So let us now just stop here in and let us continue our discussion on Wednesday. Okay? Is that clear? Is that clear? I just can see that you are already having a hard time absorbing the learning. So for you to have at least time to realize, to at least absorb this kind of learning. So let us just stop here for now. But before we actually conclude the the conference, I just want you I just want you to uh, type on the chat box what did you learn on today's lesson, and what are your key takeaways in today's lesson. Please type onto the chat box. What did you learn on today's lesson? Let's see. What did you learn on today's lesson? If you have learned something or not. Okay, so I learned about phasor forms and complex numbers, how it is related to AC circuit analysis. I also learned the conversion of rectangular form to polar form and vice versa. Very good, Andrea. Using calculator in transforming rectangular complex number to polar form and vice versa. Very good, Lance. And Russell learned about phasor domain or frequency domain, the time domain, conversion of polar to rectangular form, and vice versa. Okay, very good. And Reggie, rectangular to polar and polar to rectangular. Okay. Of course, you could also at least you could also try to find out if you have different set of calculator, different type of calculator. You could at least find out or familiarize their your calculator so that you could at least use them onto our later's discussion. Okay, according to Paul, what he learned for today is how to use the calculator in complex numbers and what should I input in rectangular and polar form. I learned from today's lesson is the complex numbers and how the conversion of polar and rectangular. It seems like you already stopped. Okay, you already stopped on polar and rectangular to polar conversion. So I hope you have also learned this sinusoids, the introduction to sinusoids, introduction to phasors, how phasors and sinusoids work, what are the terms relevant, okay, the different terms that is very relevant to AC circuits, and of course the different techniques that I have applied a while ago on onto different examples that we had. So later on Wednesday we will be dealing more, okay, we will be dealing more of these certain examples. We will be dealing more of the phase difference. Okay, what are phase difference, the phase difference with phasors, the RLC circuits, okay, with sinusoidal excitation, the purely resistive, the purely inductive, and the purely capacitive circuits, as well as the impedance concept. Okay, when we say impedance concept, what are impedances? What is the difference between impedance and resistance? Okay, so I hope you could also have your advanced reading okay, your advanced reading onto our module so that later on you will not be having a hard time understanding, okay, understanding the concept. And please, as I always tell you, if you do have any questions, if you don't understand what I'm saying, if you actually need more time to absorb, need more time to understand the lesson, need more explanation to understand the lesson, please tell me. Okay? Do not hesitate to tell me, ma'am, can you repeat po what have you said? What have you explained on a while ago? Because I didn't get it. Okay? I do understand that, my dear students. Okay? So please do not hesitate to tell me that I'm going too fast or to tell me